Thanks for the introduction, and thanks to the organizing community for letting me speak today. I'm very excited to tell you all about research I've been doing with Daniel Gottesman at University of Maryland on partial syndrome measurement for hypergraph product code. And here's the archive link for you all to look at. So I'll start off the talk with some background and motivation as to why you might want to use our scheme for error correction. Then I'll introduce the stacked model and put it in context for fault-tolerant circuits. Then I'll do a little background on hypergraph product codes and the small set flip decoder. And I'll round out the presentation with our results and some open problems that I think need to be considered. So the goal we are considering, and a very lofty goal it is we want constant overhead fault tolerance with 2D local gates. And there have been a number of nice talks this week that aim to address this. However, there are a number of problems that need to be addressed to actually solve this. The first one being that to get constant overhead, we need good codes, and I have the asterisk there because we don't necessarily need good in the sense of linear rate, linear distance, but we do certainly need codes with better parameters than the surface code. And the reason for that is surface codes or codes with only generators that are local have limited code parameters. And there are these two nice papers formulated trade-offs and bounds on the rate and distance for these codes. So to get around these trade-offs for local codes, we actually need to introduce a lot of non-locality. And how much non-locality we need was quantified in these two recent papers. And it turns out that you need a lot of non-locality to significantly improve over the surface code. So that's not good in certain architectures, like superconducting qubits, where long-range connections are much harder to do than the local ones that are inherently built into the system. And furthermore, there's been a few works that prove or attempt to show analytically and numerically that naively doing 2D local codes, doing 2D local codes that have high rate is not viable, in that increasing the code size actually decreases the amount of error correction that you can do. So we have no threshold. So is our goal of a constant overhead fault tolerance not possible? We think not, and we introduce this idea where we measure the generators whose qubits are spatially distant less frequently than those whose qubits are local. So what do I mean by this? If we have some Tanner graph of a CSS code that were the qubits, and then we have x checks and z checks, what we're going to do is we're going to take this code and we're going to embed it into 2D. So for many architectures, again, focusing on superconducting, perhaps, we're going to lay out the qubits on our device in a 2D grid. So we would like to embed our quantum code onto the grid. Now, when we do this, there's going to be some generators whose qubits are close together, and we're going to deem these generators local. And there's going to be some generators whose qubits end up far apart on the grid, and these generators are non-local. Now, if we only have access to local gates, it's going to take more work to measure these non-local generators. And the reason for that is we have to physically move the qubits involved in this check together, and then we perform our syndrome measurement, and we can do the readout and decoding and all that. And so it turns out, and the evidence seems to suggest that if we do these non-local measurements all the time, the errors of performing these long-range gates adds up quicker than we can correct them. So why would we do this partial syndrome? And the reason is that if we have a code for which mostly small generators, then most of the work to measure the entire set of generators is only due to the long generators. So we have potential for significant overhead savings in this regard. So as an example, consider this, this histogram where we have radius of our generator and then generator frequency. So this is just an example of some code that could be embedded into 2D. So what we have is a majority of the generators are small, and then we only have a few that are very large. And in this plot, what I have is the percent of generators sorted versus the percent of work completed. And essentially all I want to show you is that the last 10% of generators take 40% of the work to measure. So one can imagine that as we scale up our codes and our devices, this histogram is going to get even more skewed, where we have most of our generators are local, and then only a few that are very, very large, on the order of the system size. So this right plot is going to be further pushed down, where we have the last 10% are going to require more and more work to do. And this is, again, assuming that the amount of work to measure a generator is proportional to its geometric size on the grid. So to formulate this, we use the stacked model, which was recently introduced. And the idea is that we want to partition the generators into layers based on the radius of the ball of its support. And what we want is generator frequency to decrease with increasing radius. So we want many more local generators than non-local ones. And this gives us the overhead savings that we want. So in our stacked model, the bottom of the stack is going to contain local generators. So all these generators on the bottom can be measured in constant time because they're local. And there's going to be the most of them are going to be in the bottom. And then as we move up the stack, the generators get larger, and ideally we'd want fewer and fewer as we move up the stack. And then finally, as we reach the top, we're going to have only a few generators that span the entire system. So the stacked model has a direct application to fault-tolerant circuits. And what we're going to do is during each error correction round, we're going to choose one or more layers of the stack to measure. So, for example, we have a logical circuit here, and after each logical gate in the circuit, we're going to perform some error correction. And during each error correction step, we're going to choose one or more of the layers to measure. So, for example, we have, in this first round, we only measure the local ones. The second one, we measure the local ones again because we can measure them in constant time, but we also add the second layer. So now we're adding generators that are slightly larger. And finally, after this third error correction step, we add in the entire set of generators. So at this time, we've measured the entire stabilizer group. And the idea and where we get the savings is that in the rounds where we do only this local and the lower layers in the stack, we're going to be preparing the larger ones essentially in the background. So as we do each error correction step, we're going to slowly build up the resources needed to have all the generators available at some point in the future to measure. So coming from this, there are mainly two questions that need to be answered. The first one being, is error correction even possible when you only measure a subset of generators? And then the second question is, do good codes exist that are mostly local and robust to partial syndrome measurement? And again, I have good with an asterisk because we don't necessarily need good in the sense of linear rate, linear distance, but we do need, better than surface code. So the answer is yes for the first question. That's this work. And then the second question is unknown, but I'll give some comments on it at the end. So to more formally represent the stacked model, we use this idea of masking, which was recently introduced. And essentially the idea is that when we separate the generators into layers, essentially what we're doing is choosing subgroups of the stabilizer to measure. Really what we're doing is choosing subgroups or generators, subgroups of the generators of the full stabilizer, and this is what constitutes the stacks. So as these subgroups form stabilizer codes in their own right, we can define distances for each of them, where the distance of some stack at time tt is just the minimum weight operator of the normalizer of the subgroup minus the full stabilizer group. And what we have is the more generators we have, the distance obviously gets larger until we reach the full distance of the code. So really what we're going to have is this U set, which includes all of the local generators. This unmasked set is always going to be available for us since we can always measure them in constant time. And then as we add more generators, this set T2 is going to include U as well as additional generators until we reach T3, which includes U, T2, and the remaining ones, and it rounds out the full stabilizer group. So the idea is that errors with zero syndrome on some subgroup of the stabilizer do not immediately cause logical errors, so we can afford to kind of push them off into the future and correct them later in later rounds. The only caveat is that we can't push them off too far because then they might form logical errors in the full stabilizer group. And just a notational issue that I'll mention is that when we say applying a mask, I actually mean specifying the set S minus TT. So you can understand masking as like we're masking the value of the syndrome of those generators. So how exactly do you do mask error correction? There seems to be a number of potential solutions. Maybe the most simple one is to just drop the bits of the syndrome that are the masked bits. So if we have our syndrome here, and the red ones are our masked bits, so we just drop it, and this just corresponds to a smaller parity check matrix of some other stabilizer code. Another option is that we could perhaps assign random bits to the masked syndromes, and this is just equivalent to having syndrome error on them. We could assign them to some fixed value, like 0, or finally we could treat them as unknowns, which is slightly different than the rest of the options. So it seems like this fourth one is the most logical option to take, and the reason for this is you get the most information out of this fourth one. For the first option, you're throwing away the information that you know some of the bits are masked, and you're just dealing with this decoding problem of this smaller code. The second one isn't great because, at least for the codes we're looking at, the syndrome error is proportional to the size of the error. So if we do masks of constant size, then there's going to be the decoder is going to try to guess that the error is actually really big. When in fact at low error rates, it won't be the case. This third option is better, but we again throw away the information that we do have masked syndrome bits. So this fourth one really squeezes out all the information we can get with the available syndrome information, as well as the information that we know some of the bits are masked. So now I'm going to briefly talk about the codes and decoder that we use in this work. So we use Hypergraph product codes, and essentially Hypergraph product code is it's a construction that takes two classical codes and outputs the CSS type code. And you can think about it as the graph product of two codes, where we have our two base classical codes here and here, and then as we cross them, the rows inherit the edges from this classical code, and then the columns inherit the edges from this classical code. And more specifically, we use quantum expander codes, which are Hypergraph product codes, but they're formed from good classical expanders. if you take a random classical code, it'll be expanding with high probability, and it'll have linear rate, linear distance. And as such, the resulting quantum expander code will have linear rate and distance scaling like the square root of n. So to decode hypergraph product codes, and specifically quantum expander codes, there's this nice work called small set flip, which furthered a classical result of the flip decoder. And essentially the idea of small set flip is that we're going to look in the support of opposite type generators for qubit flips that decrease the syndrome weight. So for example, if we want to look at this in the support of this check, we're looking at all the qubits that are connected to it by an edge. And what we find is that flipping these two bits is going to decrease the syndrome weight by 1. So the decoder is gonna go through each of these checks. It's going to find which flips are most beneficial to decreasing the syndrome weight, and it's going to perform that correction. And it was proven for quantum expander codes that this small set flip is very good at correcting errors, in that it can correct errors of random errors of linear size. So now to modify small set flip for masking, really all we have to do is hide the action of flipping the subsets on the syndrome. So for example, if we look in the same generator, if we flip the bits again, the syndrome decreases by 1 again. But for some errors, it's going to be a case that while they were previously correctable without masking, they won't be correctable anymore. And these are the errors that get missed in each intermediate decoding round, and we hope they get eventually picked up at the end when we unmask the full set again. So for analytical guarantees, we use results from the small set flip decoder and the quantum expander codes in the presence of syndrome noise. And what we show is that for random masks, so if we randomly mask some of the syndrome bits, there is a threshold. And I know I just said that treating the masked syndrome bits as errors is a poor decision, and practically it is a poor decision, but for the purposes of showing there's a threshold, it works out. And essentially what the original theorem says is that a threshold is guaranteed when the qubit and syndrome errors don't form large clusters on the syndrome adjacency graph. And really this just comes down to the percolation threshold of the syndrome adjacency graph. And for the quantum expander codes that we're looking at, this is around 2 or 3%. So below 2 or 3%, we have a threshold where increasing the code size actually does decrease the logical error rate. So we wanted to see if we could perhaps get better than this 2-3% threshold. And so what we did was numerical simulations, which consisted of several rounds of masked error correction followed by a single round of unmasked error correction. And I introduced these two schedules, which is a way of specifying which syndrome bits are masked and which ones aren't. And the two we looked at in the paper is this simple one where we just have some percent of the syndrome bits masked for the entire duration, and then we follow by 1 round of a full syndrome measurement. And then the second one is perhaps a more realistic one where we have some percent of generators masked, and then after some number of rounds, we add back in a few more generators, but not the entirety of them. And I'd like to mention that these two schedules were chosen pretty arbitrarily, and in reality, what would be determining the schedule is how long it takes you to measure these long generators. So with 0.1% error rate, we see here in this plot that it's actually the case. It's better than break even, this red line. It's better than doing nothing for up to 30% masked. And then, again, this is for the random mask. And one notable thing is that even for 10%, which is a constant fraction of the generators, we see very close performance to completely unmasked. So what we did now is, with increasing code size, we looked at these two schedules and determined the logical error rate while increasing code size. And what we found is that we actually get exponential error suppression even for large masks. So as a reminder, the analytical threshold is around 2 and 3%. And what we see here is that in this plot, we're plotting distance versus logical error rate per round. And what we want is, on a semi-log plot, we want to see exponentially decreasing logical error rate. And while as we increase the masking percentage towards 30 and 40%, we lose most of our error correction power, we still do see some return where increasing the code size does decrease the error rate. And these plots on the right indicate the difference in performance between the two schedules. And it's perhaps no surprise that the second one, where we unmask more frequently, is performing better. And indeed, even in this 50% mask case, the simple mask doesn't have any error correction threshold, whereas the case where we unmask more does have a threshold. So we were wondering if this was unique to Hypergraph product codes. So we looked at 2D hyperbolic surface codes, which seemed like a good candidate for this scheme as a whole. They're planar in hyperbolic space, so it seems like they might be, nicely embeddable into 2D Euclidean space in some way. And so what we did was the same sort of simulations, but instead using the minimum weight perfect matching decoder, and we treated the mask checks as boundaries in the matching graph. And what we find actually is that it's better to do no error correction rather than to try with this partial error correction. So, and this red line is trying to do 10% with the 10% masked, whereas this yellow line is just skipping entirely the syndrome rounds where we don't have the full information. So it seems like there is something with Hypergraph product codes or the small set flip decoder which allows this sort of robustness in the decoding. So some open problems is to find codes with favorable generator distributions which are robust against masking, and you can either take two routes to doing this. One might be to find 2D embeddings of existing codes, or we could develop new codes with desired locality. I'd like to point out two such potential codes. This recently introduced long-range enhanced surface codes, and then the semi-topological codes in this second paper. And these two codes essentially have many local connections, but they're enhanced by these a few long-range connections. And as such, we get a nice distribution, generator size distribution that drops off as the generator size increases. And the second one is to develop new coders that make use of the masking information more effectively. So like I said, I think the best way to do this decoding is to give the decoder all the information you have, which also includes which syndrome bits are masked, as well as the available syndrome information. So to summarize, we introduced this scheme based on the stack model for implementing non-local quantum LDPC codes on architectures that are restricted to 2D local gates. We provided analytical evidence to suggest that there is a threshold while using quantum expander codes and the small set flip decoder. And we also ran numerical simulations to show that the actual threshold you get is much better than any analytical guarantees that you can get. So with that, I'll end my talk and
Hi, Noah. Great talk. I was wondering, the plots that you displayed, they were for random masks for hypergraph barcodes, but they're not necessarily. I don't know how to arrange, for example, or we don't know how to arrange a hypergraph barcode such that some of the generators are local, others being non-local. So when we mask the non-local ones, they're not going to be random.
Right, right. That's a very good point. And in reality, what would happen is you're going to have a code, and you're going to have a fixed embedding into 2D that you want. And it is the case that there are going to be the same generators, the same long generators are going to be the ones that you don't measure all the time. And the work we did here was pretty much to show that it was essentially just possible to do this this partial syndrome measurement, but we're certainly looking at specific embeddings with where we do that sort of thing.
Hi, thanks a lot. I'm wondering about the measurement noise in your analysis. Did you include that?
No, for this case, we just did phenomenological noise on just the qubits.
Just so just qubit error. You didn't flip outcomes of measurements at all?
Yeah.
Okay. Because it seems like, I don't know, I would imagine that would be one of the main things that would go wrong in a scheme like this, would be that if you have high weight generators that you need to measure using local operations, then you're going to need to like teleport things around, and there'll be lots and lots of local gates involved to measure a single check, and so the noise would be very high on the outcomes of those particular high weight generators. So yeah, not high weight, but non-local. Sorry.
Yeah, that's certainly true, but for these codes, it's probably advantageous to look for like single shot codes, which can perhaps handle this masking as well as syndrome errors. They're kind of, they're kind of related, I guess.
I guess, well, yeah, it'll be interesting to see. I guess it remains to be seen. But I would also imagine that the redundancy that usually helps you have single shot will be lost whenever you're not measuring everything. But yeah, it's interesting to consider. Thanks.
Thanks for the nice talk. So I have a question about this threshold argument. We know, like, for the standard threshold proof, you need both the data error and the syndrome error to be like local stochastic, which basically means that your probability of error has to decay exponentially with the size of the error. But seems like when you do this like constant percentage of the masking, calculate with a constant probability, you're having a like high weight syndrome error, which is not locally stochastic. Do you have a comment on that?
So yeah. Really, you're not going to have a provable threshold, I guess, because what's going to happen is for these random masks, there's going to be a constant probability that you mask all of the checks for a single qubit. So then any error on that qubit is going to be undetectable. But in practice, I guess is the takeaway is that in practice you do see this exponential decrease. Now for the analytical proof, we treated them as syndrome errors instead of the masked bits, and for those cases we did like the probability of error is small enough that it all works out in the proof.
Okay, thanks.
Okay, thanks. I have two questions. So the first is, up to my knowledge, the small set flip decoder is for general LDPC codes. It doesn't know anything about the geometry, like two-dimensional lattice or even higher dimensional. But in your example, you use the two-dimensional lattice for hypergraph product codes. So my question is there any two-dimensional structure related to the small set flip decoder?
So the small set flip decoder is just a generalization of the flip decoder, and it doesn't necessarily depend on the 2D layout of the 2D layout that I showed or whatever you choose, it just looks through the appropriate checks and decodes it that way.
Okay. So it's basically you just throw the parity check matrix into the decoder, and so it's still general. Okay. Thank you. So my second question is, I think the masking idea, when you measure partial syndrome measurement, it's very similar to gauge fixing. For example, if you take the showcode, instead of the weight 2 checks, you measure the weight 6 checks, then it becomes the Bacon showcode. So have you think about to analyze this masking technique from the perspective of gauge fixing or subsystem codes?
Yeah, so they're very closely related. The main difference is that we're actually storing logical information in the full space. So when we do these masked, the masked bits create a subgroup of the stabilizer, whereas for subsystem codes, there's like the part where we don't store logical information, but we're thinking about ways of perhaps reinterpreting this masking as in the subsystem code language.
Okay, thanks.
Okay, let's thank Noah again. I think we're out of time for questions.